Hi everyone, my name is Petrus Swissler, and today I am presenting FireAnt3D, a 3D self-climbing robot towards non-latticed robotic self-assembly. Self-assembly in nature is a set of behaviors you see executed by certain species of social insect. Two examples of this include the bridges built by weaver ants and the festoons built by honeybees. The insects form these structures by climbing over each other and then grabbing on to their peers, using pincers and legs at seemingly arbitrary locations. The organization of these structures is freeform, in that it does not conform to a lattice, and it allows the insects to build structures that are highly adaptive to their environment. This promise of adaptability has driven a lot of research into the field of robotic self-assembly, since it would be useful in situations where the environment may not be fully understood, such as disaster relief, construction, and exploration. The way that the robots build these structures tends to differ from the methods used by insects, however. Robots tend to avoid self-climbing by using techniques such as relying on external forces, basically you shake them up and they come into contact, and using neighbors to pass them around the structure. The downside to these approaches are that they give up the ability for the individual agents to make their own decisions on how to build the structure. This means that if there's a malfunctioning agent, the structure may not be able to complete. The organization of these structures is also different from those of insects. Instead of using freeform structures, the structures tend to be highly latticed, as you can see with the robot pebbles here. They have a very rigid square lattice. The reason that lattice structures are undesirable for large-scale self-assembly is that misalignments will occur during the assembly. This can be due to tolerance stack of the assembled robots or due to gravitational deflection of the structure as it's being built. Lattice structures are also problematic if you're trying to build from two locations at once and meeting in the middle. Because with this sort of scenario, you would have to very rigidly control where exactly the robots are starting. If you don't understand the environment, this is going to be difficult to do. These issues could, of course, be addressed by tightening up manufacturing tolerances of the robot or increasing robot capability. But if you're building thousands of these robots, you want to minimize cost, and both of these options would increase cost. The reason that robots go with these lattice structures and insects go with freeform structures really comes down to the way in which they attach to their neighbors. Recall, with insects, they use their pincers, their legs, and they grab on wherever they can, resulting in the freeform structures I showed previously. In contrast, the attachment mechanisms used by robots tend to favor attaching at very specific locations. These attachment mechanisms fall generally into one of three categories. There are mechanical attachment mechanisms, such as hooks, grabbing onto specific locations. The problem with these is that the mechanical complexity of the mechanisms means that you are going to have a bit of difficulty maintaining them. Assembly is going to be a bit more difficult as well. Electrically activated attachment mechanisms avoid this mechanical complexity. But again, with electropermanent magnets and soldering, you need to attach at very specific locations in order to have attachment occur. Simpler still are passive attachment mechanisms, such as permanent magnets. The problem with passive attachment mechanisms, however, is that they fundamentally limit the strength of the structure. Consider, if I want to move from location A to location B, I must first disconnect on location A. Because passive attachment mechanisms do not have a way of lowering disconnection force, it means that the attachments can only ever be as strong as the robots can break on their own. There are certain robots that have been developed that can self-assemble without using lattice structures, and we'll go through some of them right here. There is Slimebot, which uses Velcro in order to attach whenever two units come into contact. Unfortunately, with Velcro, the attachments are rather weak. Further, Slimebot cannot self-climb. Eceton Robotica is a climbing robot that can attach anywhere on a neighbor's body, but it must first properly orient the gripper for attachment to occur. As I said, it can self-climb, but it's limited to 2D operation. The original FireAnt can attach without any sort of alignment, and its attachments are very strong. It uses these attachments to self-climb, but again is limited to 2D operation. And that brings us to FireAnt3D. FireAnt3D uses its 3D continuous docks to attach arbitrarily to its peers using non-latticed connections. It uses these connections to climb over arbitrary arrangements of its peers, using minimal sensing and control. The key component of FireAnt3D are its continuous docks. These docks take the form of hemispheres and consist of 4 layers. The top 2 are the most important. You have a 1.4mm thick layer of conductive plastic at the surface, and right below that you have a copper mesh. To attach to another dock, this dock has just contacted this dock, you apply a voltage to the copper mesh relative to a ground return hoop, which sweeps down until it touches the other dock. Current will then flow primarily along the copper mesh until it must pass through the conductive plastic. This heats and melts the plastic. It then continues along the copper mesh of the other dock and back out through the ground return hoop. When you let this connection cool, it results in a strong and rigid bond. This is what it looks like in real life. 2 docks come into contact, hoop sweeps down. Melting occurs as current begins to flow. After cooling, you have a good connection. And by repeating this process, heating and melting the plastic again, the detachment force becomes low enough that you can just lift it off. These docks are both strong and reliable. To test the reliability, we had a 3-to-1 arrangement of docks, which were attached to each other. This was just done to have a repeatable test. And we pulled it to failure. This arrangement had an average break strength of 767 newtons, which is very favorable when compared to the robot weight of only 10.8 newtons. The reliability of the docks is also good. During developmental tests, we would attach and detach at a single point repeatedly. And after 50 attachments or so, that's when you started to see the first failures, with failures becoming common after about 100. Considering the fact that you are not going to be attaching at a single point repeatedly, recall that we are not using lattice connections. Because of this, you're going to be distributing these attachments all along the surface, and so this 50 attachments at a single point is quite acceptable for the sort of stuff that we're doing. Additionally, you can always resurface these docks simply dragging a soldering iron over it. And that brings us to the mechanical design of FireAnt3D. The robot consists of 3 spheres joined at a center body, and that's one robot. These spheres, which are 85 millimeters in diameter, are entirely enclosed in the hemispherical 3D continuous docks. There is also the ground return hoop, which can sweep all the way around, allowing for attachment to occur regardless of contact location. There is also a sphere arm, which can move up and down. The robot uses this for locomotion. And that motion has a range of 315 degrees. This arm is then inserted into the center body right here. In this socket, the arm can passively swivel plus or minus 65 degrees. Remember that for locomotion. Also in the center body are 2 force sensing resistors. And so as the robot presses down on a neighbor, it can sense the force with which it is doing that. Finally, the center body has a logic board, which it uses to coordinate all of the logic boards in the spheres. The sphere logic boards contain all of the low-level control necessary to perform attachments, locomote, and basically respond to any demands from the Centerbody logic board. Each sphere logic board has a current sensor to measure current flow during attachment, as well as an arm limit sensor to detect when that arm has reached its hard stop limit. The force sensor in the Centerbody completes all inputs for the robot. The outputs are similarly simple. Each sphere can control its attachment, basically controlling its voltage and hoop actuation, and it can control the motion of the arm. For both of these outputs, we simply use bang-bang control. And that brings us to locomotion. In this example, the robot has just flipped about sphere B, and it wishes to flip about sphere A. Both A and B are attached to the white spheres shown here, which represent other robots. It first detaches sphere B, heating and melting the connection and lifting free of the surface. It flips forward until it executes a preparation step. Recall that the arm cannot rotate endlessly. It's limited to 315 degrees, and so it needs to do this. And it continues flipping forward. At a certain point, dock C contacts another robot. Now recall that you have that passive degree of freedom, and so as you sweep down, that pivot will allow for 3 points of contact. At this point, the robot decides which direction it wants to move, either C or B, or go backwards. This is how the robot steers. In this case, it has decided it wants to attach on dock C. And let's take a look at it in real life. Here is the robot walking on a floor of its piers. Here it is walking up a wall of its piers. The tether you see is simply for remote control. The robot does not make decisions on which direction it will move, instead relying on a human operator. And here it is walking on a ceiling of its piers. Note that the method of locomotion was exactly the same, regardless of the orientation of the surface it was climbing on. Also note that there was no alignment or complex motion planning that was occurring during locomotion. FireAnt3D and its continuous docks address many long-standing challenges in the field of robotic self-assembly, including those of attaching to neighbors, locomotion, as well as a move away from lattice structures. FireAnt3D presents a profoundly different method of approaching the robotic self-assembly problem. The robot can walk over arbitrary arrangements of its piers without the need for alignment to these robots and without the need for complex motion planning or control. Future swarms of FireAnt3D robots will be able to form the sort of non-lattice structures shown here, and we hope that the research outlined in this paper provides the impetus towards and means by which to further explore non-latticed robotic self-assembly. Thank you all for your time.